Okay, so as far as the last class discussion, we discussed up to what is Flynn's classification, what are the part of your different classifications we have, and we had looked into that what different kind of classification they are. Anything anybody need to ask in that part? What is NUMA? What is UMA? Everything we had discussed yesterday. So, uniform memory access, non-uniform memory access, we discussed. Now, based on today's discussion here, we can find out that what different way we can go for the part of your concurrency to achieve. There are different ways we can go for, and that could be uh, discussed based on the part of your uh, uh, possible ways that we can. So first one is the dependency graph, or we can say the part of your parallelism graph. Then we can go for data, how parallel they are during the execution. Then we can say functional parallelism. Then finally we come to pipeline. So pipeline will be available in the fourth unit of it. So we can go one by one that how we can go for the precedence graph or dependency graph, then data parallelism, and finally go for the functions. Now come to the part of your dependency graph. So dependency graph is also very popular as precedence graph, where it must be a directed graph and vertices are supposed to be representing different part of the task. Is the slide is visible to you? Hello, hello. Are you all there?
Yes, sir.
Is the slide is visible to you?
Yes, sir.
Okay, okay. Thank you. So here in this part we can say that what kind of different directed graphs we have, and that directed graph can possibly take you to a part of your vertex or a part of your edges, and where we can able to identify the vertices to be as the task and edge to be the dependency. Remember, this dependency, whenever flows from one end to other end, they definitely tells you that which one has to be executed first and which one has to be executed next. So age from one unit to other unit. That means to say, if you can able to draw a line from U to V at that particular point of time, we can understand that the task you must finish before the task you are going for. So here we can say age from U to V. So I can possibly go for like this. We have U, and we have V. This means that you must be finished the part of your age from U to V. That means that task you must be finished before the task V we can start. So we can possibly go for all different tasks to be completed in this manner. So if you go for the task V to start, then definitely the dependency graph will say that you must be complete before that. So you can see we have to turn off the system. We have different names. We can go for we can go for ages, we can go for bids, and check if of the particular part of the job to be completed or not. So they can be completed once, then we can able to say whether the system can be completed or not. So these are three different files I had taken, and if you go for these different files to work with, you can possibly check whether they have to be completed first or their dependency has to be completed first. So we can possibly identify that how a dependency graph will work, and we can go for the execution. Then comes to the data parallelism, the second task. So here, all the tasks you are using for, they must be applied and the part of your same set of operations to different data. Likewise, iterations. So for uh, 0 to 99, what I want to go for, I want to go for a of I must be equal to b of I plus c of I. So this will be repetitively done, so that we can go for the execution 100 times, and the operation may be executed concurrently. So we can go for the execution likewise. So this must be accomplished by a SIMD, or we can say array processor, having an active processor executing different operations in a synchronously, or we can say according to the synchronous manner. Now this can be much easier whenever we are thinking that this would go for the part of your execution with respect to some other possible task, which can be a part of your number of times you want to execute. So task of each processor can be divided between different processing elements, and they can be executed one after another in a concurrent manner. And there also we can go for MIMD to test also. But in MIMD this cannot be synchronous, because each of the processors available with a new clock, and they to bring the synchronous in between them is really difficult. So that's why MIMD is slightly different. And as far as the requirement, I discussed also what may be the difference in between SIMD and MIMD structures. So that I already discussed with you yesterday. So we can go for uh, let's take who is there. So here we can go for the part of your execution with respect to a different possibility of your SIMD and MIMDs to achieve maximum parallelism for us. Then go for the part of your MIMD. Further, we can say the processor whenever try to execute the instruction may go concurrently, but they do the execution asynchronously. Remember, in this we can find out different blockwise operations to be done in a synchronous manner by implementing the Lampert's logical clock. So normally in case of a MIMD or on a multiprocessor, if you try to work with a synchronous format, so what I have to do, I have to work with logical clocks rather than using the physical clocks. So multiple identical events can be taken care of there with respect to the part of your executions. This is what we have in case of your data parallelisms. So we can go for the parallelism feature. Let's take we can go for the part of your different processors to perform different computations. Computations can be performed either synchronous or asynchronous, and we can able to go for the grain size, how average number of computations are performed between the communication or synchronization steps. So you can see we can go for the part of your textbook based on your parallel computing that is written by Quinn. Says that here, if you go for SIMD computation, it is considered to be very fine grain, but if you go for MIMD parallelism, it is usually considered to be medium. And we can say medium grain because it may have different challenges, like how to bring the consistency in between the data during the parallelism, how to bring the global classification of the time with respect to different clock. So this kind of particular problems are there in case of MIMD, data parallelism situation. When it comes to the functional one, this is the third one, which normally discussed under on the part of your different job parallelism normally. If you ask for dependency, so here also we have dependency. You can see A tends to 2, B tends to 3, and here we can able to calculate M, which depends on A and B. And here also, if you go for calculating S, that is also depends on A and B. Now you see, if you are going for calculating the V, that is also depending on A and B, and directly depends on S, where they are indirectly on, or we can say explicitly depends on the value of A and B. So that will be also a functionality or control job dependency with respect to different calculations. So this also be there in case of the data paralysis. But controls are completely depending on the program perspective what we are working with. So with that we can able to execute them either concurrently, or we can say we can able to execute them as per the synchronous or asynchronously. So control parallelism feature is one of the best feature, but at this particular control parallelism, we have a challenge that how to divide the particular task into multiple number of identical tasks so that we can have better parallelism. So we can go for the task to be divided between the processors so that workload can be balancedly given to every processor. That should not be imbalanced process load, and parallelism can be achieved in a better way. So that's supposed to be called as the part of your post grain. So we can discuss that how we can able to go for the fine grain, how we can able to go for medium grain, we can also go for coarse grain. So this parallelism is also there with respect to how better way you can able to divide the part of your dependencies from one to the part of your other processors we have. How better we can able to divide, not only divide but also in a balanced manner we can able to uh, give them to all other processes also. So we can go for the data dependency with respect to the job parallelism. Now we will club together. So we can go for according to that with a realistic job requirement, where parallelism can be viewed that all the branches whatever we are executing, they are different tasks, and here path from one particular vertex to the other particular vertex, then job parallelism can be used to execute the task U and V in a concurrent manner. Whereas in the larger task, we can able to subdivide this into smaller identical tasks, and the data parallelism can be used to execute this subdivided task in a concurrent manner. So this is what normally happens in case of your control parallelism, where we are thinking that let to divide the particular job in between different processes and then keep their dependency in between the processors, and having parallelism is a real challenge over here. So we can go for the next one that's supposed to be the pipeline. So this pipeline is a concept where we can go further, or we can say deeper into the part of your execution, or deeper insight to the part of your execution, where we can understand how more better manner I can able to achieve the parallelism. So divide a process into stages. This is the concept behind pipeline, and each procedure must be executed several items in a simultaneous manner. So we can possibly say that here I would like to prepare the car architectural assembly line. So where we can able to understand those. First, we have to check for the preparation of the baseline with the part of your wheels. Then we had added here. You can see the baseline of different structures of seats, then we can go for designing of the outer panel, then the final design will come. So this supposed to go for one after another. But if you look into here, the achievement of the requirement, how simultaneously they are working. So you can see how 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 simultaneously we are working here in this particular platform. So how number of times within one single cycle we are working, and this can able to achieve better or more and more platform friendly requirements, and we can able to understand how better way this parallelism can be opted out. So this could be much powerful in case of your discussing two pipeline stages. Now, if you really wants to go for the part of your consideration uh, of your pipeline concepts, we can go for the let's take I will go to uh, just a minute. I will go to here some further calculations in pipelines. Let's see. I will go for here. So if you look into that, how best way the pipeline architectures are came into picture. So this is the part of your pipeline architectures are came into picture, as I had discussed yesterday. So we have Flings classification, we have Feng's classification, we also have handler classification. And I told you regarding the Feng's classification with respect to the part of your possibility of serial and parallel processing. So here in this case, we have to determine that how better way the Feng's classifications can go for a serial or parallel processing. So if you imagine at this particular point, the data whatever it is going to update, or we can say the data whatever it is going to read, in what manner. If you think of what manner they supposed to read this, you can see either they can go for bitwise, right? See, this is a matrix format of your data stored. How it is going to read, you can see either bit way or either word way. So here in the first format, if you will say that bit format, to make it parallelism, you can read one bit of each word. So you are parallelly accessing multiple data sets. But in other way, if you go for the complete word, I would like to say this is the part of your word access. So this is supposed to be done in two different way. One can be called as the part of your serial processing. So serial processing is the word one. So that's why bid processing or word processing, or we can say single word at a time. But if you go for the parallel processing, they will come to the bit processing here, and this bit processing will say at a time multiple number of data we are accessing, and that could be much faster in comparison to the serial processing. So it can be go for a bit slice to work, bit slice to work, or a part of your word slice. So either of the way, if you go for, they can possibly find out their solutions. Okay, so that in case of Fink's classification, I can able to know that whether I will go for the word slicing, whether I will go for the part of your bit slicing process. This would be the part of your Fink's classification. Now, if somebody wants to understand that what kind of particular requirement we have in case of handler classification. So here also I can possibly say handler classification is only to remember at this particular part of your time. If you go for handler classification at this particular point, I can able to remember that what data you are taking with respect to the degree of parallelism you have. So here I am checking for that how many different number of work you are doing at one point of time. So this is your degree of parallelism we are checking, and this degree of parallelism can be uh, a task with respect to the number of instructions you are executing. So this could be the part of your one way also, where we can work. And this also test that whether we can able to go for a, I guess, a maintenance of the degree of parallelism or not. That means number of processes completed, number of process must be entered into the processor so that we can maintain the degree of parallelism with respect to the part of your necessity. So these are different classifications based on which the pipeline can be achieved. Let us go for the pipeline concepts to understand. So this is what the Flynn's classification based on which the pipeline has to be designed normally. Yesterday I told this is your single instruction, single data. Then go for the part of your SIMD processes. So SIMD processes to work with the part of your different processing units, and then come for the MIMD with respect to the part of your multiple number of processing units with multiple number of control units. Now if somebody wants to classify these particular systems in further, then we can possibly told you that how we can able to understand in between the centralized system and the part of your decentralized system. So this supposed to be your UMA that I told yesterday. This supposed to be the part of your NUMA as far as our discussion. Now coming to the implementation of the parallel computing, now we can ask for that whether we can go for a strong definition to make it more than one executions or not. So what I want to make use of. So either I would like to go for a very high speed processor. Either I will go for a pair of high speed processors. I have to go for more number of pairs of high speed processors of what I really need. Now here basically we ask for a task also. If I go for a printing task, I would like to ask also that this printing task will measure you in what manner we are going to execute. That means I have red color printing, I have blue color printing, I have black color printing. So what you suggest at this particular point of time? Should I go for the all different part of printings to complete one after another, or you suggest that I will go for different executions one after possibly. So should I go for the first one, or should I go for the next one? So you can read out here what we have in these cases. Should I go for the first one, or should I go for the second one? Either of the situation. So each set should be printing red, then green and blue, or else we can able to go for complete all red, then complete all blue, and then we can go proceed next. So in the first one, if you look into, we can say maximum switchings will be available. So maximum switchings will kill your time, though you are going for a parallel computing. But in this case, if you go for the second one, that will save your time. We can minimize the switchings of colors so that we can able to go for one after. So this scenario will let you understand that what I told yesterday, how you can able to differentiate between the processing and concurrency. So the processing with respect to the parallel and the concurrency with respect to the execution is really different from each other, so that we can able to identify that whether each parallel can be called as a concurrent, where each concurrent cannot be called as a parallel. So this I told you yesterday, and what are the reasons behind. And depending on that, now you see what are the different possible levels of implementations I would like to go for. So in levels we can say the first level, second level, third level, and so on we have. But I would like to tell, in the levels I can go for the program level, that go for the algorithms. Then come for the procedure levels, we can possibly have softwares, we can go for instructions, and finally we can come for intra instruction levels, that is depending on the hardware. So these are different possibilities of your task executions with respect to different possible levels we are going to make use of. And now here the parallel computer structure came before you. So parallel computer structure also came before you with respect to three different names. I can possibly go for the part of your pipeline computers. I can possibly go for array processors. I can possibly go for multiprocessors. Remember, if you go for any of these processors at any point of time, they can very well strategically designed for your parallel computings, for your parallel executions with respect to the time, with respect to the part of your computations, with respect to the demand of the user. And that's why at this particular point of time, if your pipeline computer will work, they can possibly go for a temporal parallelism, where a array processor works, they're supposed to work for a spatial parallelism. And if you go for multiprocessors, they're specifically designed for the part of your asynchronous parallelisms. So we can go for the first one, the pipeline computers, with respect to different possible task of temporal parallelism. So temporal parallelism is supposed to identify or exploiting the scalar entity. As I told yesterday, if I go for a equal to 5, I told you this yesterday, that I want to go for a equal to 5, I want to go for a of 5 equal to 1, 2, 3, 4, so 5. So here makes the difference in between the spatial, in between the part of your temporal parallelism. So we can go for bringing the instruction. So task has to break into multiple stages and it will work. And here, whenever we are bringing the task, we are bringing more number of tasks at a time, and they can be faced one after another. And if you go for the part of your array processors, and this array processors will say duplicate hardwares to perform multiple tasks at once. So they have different possibilities, and that's why the spatial parallelism need to bring the complete array, so that when multiple number of hardwares performing their multiple tasks, if they require multiple amount of data, they can definitely provide it from it, and we can able to save the time of access. So that's why here the scalar and vector exploit their computation times, and further they try to achieve a better parallelism. But at the same time, if you are coming for the multiprocessors, it is slightly different. If you are coming for the multiprocessors here, we are supposed to asking about the time. So time is not globally available here, so we are having different set of instructions in control units, and every control unit have its own master clock. And having different clocks, talking about a global time is really not possible physically. So if you go for a logical clock, then only we can bring the synchronization, or else not. So that's why a multiprocessor works asynchronous parallelism, with interacting to every processor in a shared resource. We can able to go for message passing models, we can able to say shared memory. So any concept, if you say, both are working for the part of your multiprocessor systems. So in parallel computer structure, if you go for parallel computing, these basic three structures we have to discuss for. So we can remember these particular things, that how come they and exploit parallelism in terms of pipeline computers, in terms of array processors, in terms of multiprocessors. Let us have a look to each one. Now, if you go for a pipeline computer, normally we believe that instruction fetch we have to go for, where we can able to fetch the instruction from the instruction memory. Then I would go for instruction decodation. So here I have to decode the instruction with respect to a encoder and decoder, which will read that what kind of instruction it is. Then coming for the part of your operand fetch. So fetch the operand from the data memory, and then finally go for the executions. As I told, the instruction is divided into multiple number of stages. So here we have different number of particular segments to execute, and this multiple pipeline cycles will go for a defined time to execute each of these phases. So we have to find out a pipeline clock cycle time which can set equal to the part of your slowest stage of among these four. So if you say that this will go for the part of your 30 unit of time, this will go for the 20 unit of time, this will go for 10 unit of time, this will go for 40 unit of time. Now we can say the 40 unit is the slowest one, so that will be taken as the pipeline execution time, because here we have to go for the part of your parallel executions with respect to others. So parallel executions with respect to other we can say here, each one will be having a synchronized clock cycle time. Why it is possible? I have a common clock. Every stage is under a common clock. It's a uniprocessor implementation, so that we can able to synchronize every common clock, and we can come to a suggestion that what we can able to implement over here, and then we can able to go further processing. Now, there are the different possible latches in between each of the particular implementation, and these latches will work what? They will store the intermediate results in between. Now comes to the complete pipeline structure. If you want a scalar, I have scalar. If you want to go for vector, I also have vector access. Now you see, I have my memory access, and here the scalar fetch and vector fetch will go for the memory to fetch the data. So it can be your instruction, it can be your data on the operand fetch. So either of the case. So I had made the vector and scalar individual access to it depending on the control. So these are the control lines. You can see the dash lines are control lines, and straight lines or full lines are supposed to maintain your data flows, whether it is instruction, whether it is a data operand. So this can be floating its value from 1 to n. So we can start with the fetch, then go for the decodation. Then during the operand fetch, I will try to look into either of the case, whether it is a scalar fetch or vector fetch. Then the scalar pipeline or vector pipeline will go for its instruction execution one after another. So this is completely based on the choice where we can go for the executions. So, oh, I thought anybody joined. Okay. So here, in this case, we can go for the part of your execution, and this execution must be uh, in a part of your pipeline structures. How your pipeline looks like from the internal perspective of the view. If you want to access a data from the vector, if you want to access a data from the particular scalar, so you can see the difference of registers. So scalar register is simple general purpose register. A vector register is supposed to be a vector pipeline register. So that makes a difference, that who can able to store what. So vector register may be a buffer type, whereas a scalar register is simply a general purpose register we can consider for. Then we can proceed for the part of your array processors. So this is your next discussion to available with array processor. Array processor is one of the particular demand with respect to, we can say, in the Flynn's classification, that is SIMD, SIMD processor normally. So what we have synchronous parallel computers. We can go for replications of ALU systems, and then we can allow these replications of ALU systems to work at a time. And only one control unit is there to control them all at one time. So I can go for fetch, I can go for decodation, and next we can go for the associative processors to work. So let's see how do it look like. Now you can see these are all processing elements for you. Sorry. So these are all processing elements here. We have one processing element and n number of processing elements. So every processing element having a processor and a small memory, that is your buffer, and everybody has to be connected to a network. I will tell you regarding the network structure, how they go for the connections. What are the different network structures here? So with respect to which we can able to get connect with different processors. So we can go for the interconnection network, which will provide a common access to every processor, and we can come to a point whether the data can be consistent or not, whether the data written to the processor is consistent or not, and so on. So here we can understand that the scalar processing definitely looks into the control unit for the control. But remember, every control unit must kept one control memory, and this control memory must be storing all the source codes and supplying the source code to the processing elements so that they can able to do the job. So theme behind it, duplicate hardwares that performs multiple tasks at overlapping time span. So we can possibly say this is also a parallel computing system called as the part of your, we can say, uh, array processors, or we can say the Flynn's classifications SIMD array processor. So in many books, if you read also, they write SIMD array processors. Then compare to the next one that's supposed to call for your multi-processing systems. So here every system is different from one another, and we have a local memory, we have a IO device, we have a part of your different clock, and this can be the part of your shared memory throughout the interrupt network we are working with. And we can go for the part of your any interconnection network, time shared, crossbar, multiport, or anything. So that could be the part of your interconnection network part, so that we can able to interact with each of the processors. So here you have both the flavors. As I told yesterday, I can go for loosely coupled. So that is your NUMA. You can go for tightly coupled UMA. It is your choice which one you want to go for. So you can see here the multiprocessor. So you have a shared memory concept. Every module will go for a single writable memory module, but readable to all. As I told you yesterday, it will write to a specific memory memory protection, but whenever they want to read, they can read the complete memory. That's why it is a shared memory. And every processor is connected to a interprocessor memory connection network, so that we can able to retrieve the data from one processor to other processor to maintain the dependencies. If you want to go for maintaining the dependency from the part of your processor 1 to processor 2, because I told you in data parallelism we are dividing. In the control job, I told we are dividing a job into multiple number of jobs. And if you can divide a job into multiple number of jobs, what is going to happen? Here one job is executing on one multiprocessor, other job is going to execute on another different multiprocessor. So if you are executing from one to other, then if they are not communicating, then passing the data which we calculated on P1 and forwarding it for the next execution is not possible. So we have to be with a interconnection networks. And remember, every processing unit now we have a local memory, that is your main memory. So multiple main memory we have. To bring the consistency of the data in multiple number of main memory is really a challenging. We will face inconsistency, data inconsistency problem here, and this can be brought to a conclusion only by interconnection network. That means if you have some inconsistency, you have to look into the invalidate protocol for that data. That means that data is no more used after calling the invalidation protocol. No one will use that data. So what will happen after that? Whoever having the most updated value of that particular data, they will broadcast to all others. Then we can able to call for a broadcast protocol. So invalidate protocol and broadcast protocol can be possible through the network if they are connected to the processor local memory, and then they can bring the consistency among them. So it is not that the only we are providing a communication through the network, we are also bringing the consistency between the data in different local memories. How we can able to bring the data in consistency. So we can go for a invalidation protocol, we can go for the part of your what broadcast protocol, so that we can able to bring consistency in between different processors local memory. That is one of the best way we can do it. So this is what we have. We can go for the implementation of your flinch classification here even. So we can say this is MIMD processors. Then then go for the getting into the parallel executions platform. We can possibly look into that what we are achieving. I told you what we are achieving. We can go for the instruction level, that's called as fine grain. We are getting in the pipeline system. So individual instruction we are executing, and then we go for the part of your individual instruction threads to execute, and threads are executing in different ways. Then if you go for the thread level parallelism, that means to say the medium grain. So different threads of the processors are executed parallelly. So that's supposed to be a medium grain. And then finally comes to the processor level, that is your multiprocessor. Different processes can be executed parallelly, so we can able to go for the close grain. So here we can say how the levels are increasing from fine grain to medium grain, from medium grain to close grain. So this kind of parallel activities or parallel execution, parallel computing activities of the programs we have. Then coming to the part of your temporal and spatial, I already told. And depending on the exploiting in pipeline or depending on the exploiting in SIMD or MIMD, we can make use of, so that we can able to achieve data parallelism. So how we can able to achieve the data parallelism? That can be by temporal or that can be by spatial parallelism. So this is what elaborates that how we can able to go for uh, pipelining through different pipelining structures. So next to discuss about ILP, instruction level parallelism, that I want to execute about fine grains. So what better way these fine grains can be implemented? Now you look into that the time calculation. I want to do the time calculation. That's why we have to look at. So a pipeline always incorporates the concept of overlapped execution. Let's see how it executes. So we can possibly go for a approach that how students are admitted into a batch in a 4-year system of format. Every year admission is going on. It's not like that one batch will admit, then they will passed out after 4 years, then new batch will be admitted. No, every year admission is going on. So I told you something we have to work in a iterative manner. So we can say admit one batch, then next batch will be admitted after the first batch will completed their course. That is not the way the pipeline works. So second one we do admit students every year, and the second one approach is much better, and the average student graduating per year increasing 4 times if you go for the part of your execution timeline. So you see the execution timeline. So you can see here, first year, again, one particular task admitted, then you can see they go to second year and a new batch will be admitted. Then the first batch will go to the third year, second batch will be go to the second year, and a new batch will be. And then we can go for achieving the final output, the maximization, the 4 times. First batch go to fourth year, second batch go to third year, the third batch go to second year, and you can see here one new batch will be again added, that will be in the what, first year. So you see how the speed of execution is increasing. Now, according to that, at this particular level, we are always increasing the task. So which level we choose, the maximum level where the maximum students are available. So pipeline, increasing the task time to time, go for the execution pipeline. So if you follow, if you go for MIPS pipeline, let's take, if you go for the part of your MIPS MIPS pipeline. So this example was given based on the MIPS pipeline, and I followed the example from the amateur book, which supposed to be in a fine grain from the part of your requirement. So this was also followed in Patterson also, parallel computing using Patterson. So this followed, we say that we have to go for the fetch, we can go for the part of your decodation, we can go for execution, we can go for memory, we can go for write back. So this will write the result, and we can able to understand where we can able to achieve maximum parallelism. So anybody can say that in which level we are going to achieve the maximum parallelism to identify. So this is my first time clock, this is my second time clock, this is my third time clock, fourth time clock, and fifth time clock. Now you can see in the fifth time clock, the maximum involvement of the task will be there, and here I can able to achieve maximum parallelism for the execution. So this can be the part of your execution each time we are going to elaborate, and we are going to executing. So how you can able to go for the mathematical calculation? I'm just saying, you just look into. So at fifth, you can see after one clock cycle, how many executed? You say no. After second clock cycle, how many executed? You said no. After the part of your third clock cycle, you said how many executed? No. After fourth, how many executed? You said no. But at this particular point of time, when it comes to the fifth clock cycle, so at the end of the fifth clock cycle, how many instruction completed? So suddenly I will say that my first instruction completed. So here, how much time it will take? So we can remember here that the first instruction will take how much? That 5 clock cycle. So here also we have 5 number of stages. So 5 clock cycles for how many stages? 5 stages. So for 5 stages, we got 5 clock cycles. So this is the region, if you can. So if you make it 4, it will becomes 4. So it will take 4 unit of time. So first instruction will take that for 5 stages, and stage will be always represented as k. So we can say that first instruction, first instruction will take how much time? K number of time. So k is what? The stages. The pipeline, or we can say pipeline stages. This will go for the part of your pipeline stages. So if you go for the first one, if it takes k stages, I can easily understand that in the sixth clock cycle, what is going to happen? So anybody can able to tell me on completion of the sixth clock cycle, what is going to happen? Next instruction going to complete. So here this will go for the part of your instructions to complete. In the seventh clock cycle, it will go for the next instruction to complete. Now you see, after fifth clock cycle, on every clock cycle, if you look into, after the fifth clock cycle, if you are looking into here, I can possibly say, if you go for the execution, this execution definitely be there with you for execution. And this will go for execution, because we can able to do the execution after every clock cycle. So one execution takes five clock cycles. Second execution takes one clock cycle. Third, one clock cycle. Fourth, one clock cycle. And you can see that every clock cycle will give you one result. Every completion of the clock cycle will give you one result. So if I consider, I have n number of tasks. I have n number of tasks. How many I had completed? Only the first one I had completed. And I understood that after completion of every clock cycle, one result will come out. So the time calculation I can do, and here we can say, after first clock cycle, how many left out? So n minus 1 task left out. For n minus 1, how much time it will take? It will definitely take n minus 1 time for the execution. So we can able to develop the common formula for the pipeline execution time. So for the pipeline execution time, what is that? It will take, for n number of tasks, it will take how much time? K plus n minus 1, where k is the number of stages, where n is the number of tasks. So here, this would be the calculation of your pipeline with respect to achieving a parallel computing system. So that's why the pipeline system will be much more faster, or we can say fine-grained system for our need and facts. So this calculation is understood. Anybody need to ask any question? Okay, so as per the pipeline executions, whatever we are coming for, we understood that the pipeline executions will give you a better, and we can say better with respect to the result. Now coming to the other advantages, where we can able to get the system. So I would like to show what exactly a synchronous is. So you can see the synchronous, how it looks like with respect to the pipeline. A synchronous is supposed to be the synchronous pipeline, where we understood that in between every stage, this is one of the stage, this is also one of the stage. In between every stage, there is a latch available, and this latch is going to decide what we want to keep from the previous stage. So whatever we executed here, that we store in this latch. So if you are storing in this latch, they must be driven by a clock. As for the pipeline system, I have a single clock, and this can be very easily synchronized by a single clock. So all the particular part of your clock cycles are synchronized with respect to the latch, with respect to the stages. But if you are coming for a asynchronous one, that is your multiprocessor, here the multiprocessor works. So what we can say, every stage must be driven by a different clock. So that's why you can see, I have to go for a ready status. I will request for the ready status, and this ready status will give me a reply. Then only the input can be given. So every stage must go for this ready and acknowledgement, ready and acknowledgement, ready and acknowledgement. This normally supposed to be called as a handshaking protocol, and this handshaking protocol normally keeps you in a fact of execution, where we believe that the asynchronous execution always not that much easy in comparison to the part of your synchronous we have. So I told you, instead of going for a part of your physical clock, it is better to go for a logical clocks. So in distributed parallel computings, we say the logical clocks are much better for multiprocessors in comparison to the part of your physical clocks. So this is what we have in comparing with the asynchronous pipeline to the part of your synchronous pipeline we can go. So this is what how we can able to achieve the parallelism with respect to the computing system. So this is what the part of your pipeline concepts. Now, if somebody asks that, uh, can we able to go further? Yes, we can go further here. But what that can be called as? What that can be called as? If somebody asks, I would like to say the pipeline is further implemented. So here, I would like to tell you few things that if I go for a pipeline concept with respect to further needs and facts, here I can say a pipeline will be again and again classified. So that's supposed to go for the part of your super pipelines. So we can go for the part of your super pipelines. Here I can say that in pipeline, what we do. So in pipeline, if you look into in a pipeline system, in a pipeline system, what we are working with, we are going to divide the instruction into multiple stages. So this multiple stages we have in a pipeline system. But if you look into the part of your super pipeline, if you look into the part of your super pipeline, what's going to happen here? We have fetch, we have decode, we have to go for the part of your memory, we have to go for the part of your executions, and we have to go for write back. So in this case, if you are going for a super pipeline, we can go for the pipeline unit. This particular stage is further pipeline in multiple stages. So we can say here, you just look into what I am trying to say. This is my fetch unit previously available. Now what is going to happen? This fetch unit will be further divided. That means here instruction fetch, here also instruction fetch. Now we meant to say here fetch will not take complete one cycle. Sometimes fetch will not take complete the clock cycle. The thing behind it, that many of the jobs completed their work before the time expired. So if they are executing before the time they expired, then definitely I can push some more job to them. So here, instead of going for single instruction fetch, I can go for multiple instruction fetch. So the pipeline stages are further pipelined. It's supposed to be called as super pipelines. So these super pipelines will be much more faster in comparison to the part of your pipeline systems. So you can see here decodation is also divided further. This is second part. Then we can go for memory. So at this particular point, this memory unit will go for the part of your first instruction. Then we can go for the next. This is your third cycle. Then I can go for the part of your instruction execution, fourth cycle. Then write the result to the memory. So this will go for fifth cycle. Now you see, as we know that every clock cycle time is taken according to the slowest CPU stage. That's why we think many of the jobs are completed before the execution. If this happens, many of the jobs are executed before the execution, I can possibly expect that I can able to do something more task in the same time. So fetch will be taking two fetch, decodation will be takes two decodations, memory will take two memory, and so on. So your pipeline stages are further divided. That's supposed to be called as super pipeline systems. So this will be much more faster. Now, if it is a super pipeline, I can possibly go for the part of your concept supposed to be called as superscalar. So superscalar is also there. Superscalar is another concept, but not that much faster. So we can possibly say, so superscalar is also a superscalar pipeline system. So this is supposed to be called as superscalar pipeline system. So the concept is just different. So here, instead of going for the part of your further division in your pipeline stages, I can able to club two different instruction together. And here you can say fetch, here also we can say fetch. That means two different, this is called multiple instruction execution within single cycle. So multiple fetch we can say. So first clock cycle, parallelly two different instructions are executing. But remember that one constant is there. If these two instructions are dependent to each other, then I cannot able to execute that. And because dependency will not allow them to execute parallel. So if they're independent to each other, they can easily execute one after another. So we can possibly go for, sorry, not one after another. They are going to execute parallel. So I can go for decodation. Decodation. I can go for memory. I can go for the part of your memory. I can go for the part of your execution. I can go for the execution, then WP, then go for the WP. So this is what we can say that pipeline, super scalar pipeline system. Question will always ask, what is the difference between pipeline, super pipeline, super scalar processors, with respect to their parallel computing timings? So the first one we can say the as usual pipeline system, that means instruction divided into multiple number of stages. And second one is supposed to be the super pipeline. Here the pipeline stages are further divided into multiple number of stages, and then come to the part of your executions. And finally we can go for the part of your superscalars, where we can understand that multiple independent instructions can be executed together. So this is supposed to be called a superscalar processors. And this superscalar processor is one of the implementation of your multiple instruction execution. We also have a competitor to the superscalar that's supposed to called as VLIW. We Yesterday I am telling regarding this, a very large instruction word. So here also I can able to do the execution, but this happening of execution will go for a bundle of instruction together. But remember, the bundle of instruction, whatever they will execute, all are must be independent instructions. Then only execution can be possible. So they are the part of your dependencies. But in this case, that dependency is not there. We can able to omit it. So I can possibly say VLIW is also one of the competitor to the superscalar, where also we can able to go for multiple issue of instructions with respect to superscalars. So this is what we have here as far as the part of your pipeline concepts, as far as the part of your different possible structures of pipeline with respect to the parallel computing architecture. So this is for all for today's class. Anybody need to ask anything? Yes. Any question? Anybody need to ask? All of you written your roll numbers. Chinmay Ranjan and then BN Misra. Okay, BN Misra. Shraddhanjali, are you there? Shraddhanjali? Yes. Hello. No. So somebody is there. DM Puran.
Yes, sir.
You can write your name and roll number.
Oh, yes, sir.
Okay, in the chat. Okay. Thank you all.